Hey guys, welcome back to another video. In this video, we'll be solving a few electrochemistry questions. So let's start off with the first one. It's from November 2022. So yeah, the question is, data should be selected from table 3.1 in order to answer some parts of this question. Okay, all the information are given over here. Standard electrode potentials are measured under standard conditions. Okay. Describe standard conditions used in SN4 plus and SN2 plus half cell. So the standard equations are basically the standard temperature, which is 25 degrees Celsius or 298 Kelvin. The other condition is their concentration needs to be 1 mole per dm cube. There is another condition, if I'm not wrong, which is the pressure needs to be 1 atmospheric pressure, but I guess they don't need this. They want basically these two informations, and these are, I guess, mentioned in your book as well. So the temperature, which is 25 degrees Celsius, and the concentration, each of which is going to be 1 mole per dm cube in the half cell, right? So if this is the half cell, in this beaker, you're going to have 1 mole per dm cube of SN4 plus and 1 mole per dm cube of SN2 plus. Great. So question 2 is asking you, complete the diagram below to show how E0, the standard electrode potential of this and this, can be measured experimentally. Your diagram should be fully labeled to identify all apparatus and substances. So basically what was given to you is these two beakers were given, and you basically have to draw a label diagram and show how the entire process works. So first of all, a few things you need to notice is, since this is a solution with both metal ions, metal ion half cell, this is a metal ion half cell. So in this case, you're not going to have let's say a tin electrode, but you're going to have either a carbon electrode or a platinum electrode. Platinum is appreciated more, I guess. And the electrodes in both of these cases, the reference electrode and the metal ion half cell, in both of these cases you're going to have a platinum electrode, right? You have platinum metal over here, and this is a platinum wire. Good. So this is a platinum electrode as well. Okay, now the point is what else do you label? A few things to notice: the concentration of the tin, both +4 and +2 ions, and the concentration of the acid or the H plus ion, and then you also have to label the salt bridge. Good. And they're also going to give you a mark for the voltage. So these 4 or 5 things, if you label, you're going to get all of the 3 marks. Oh, plus you have to show this as well, the side where the hydrogen gas is entering. So yeah, that's it for the diagram. It's pretty simple till this. Next we can move on to question 3. So question 3, what are they asking? Equal volumes of 1 mole per dm cube of SN2 plus and Cl minus are mixed. Now use relevant E0 values to explain whether a reaction occurs between these two ions. So yeah, it's not really going to happen, but I'll explain why it's not going to happen. So if we look at the electrode potential values, first we need to identify where chloride ions are present and where SN2 plus ions are present. Now we have two equations dealing with SN2 plus. Basically, from this you're going to ask yourself, which equation am I supposed to consider? So we're going to use both of these equations and try to deduce if the reaction is going to take place. So basically, if we compare both of these electrode potentials and this electrode potential, you're going to notice that this value is more positive than compared to either of these values. Agreed? Okay, if that is the case, chloride ion is this electrode potential, in this electrode potential equation, electrons are supposed to be gained. Electrons are supposed to be gained. There should be gain of electrons. Gain of electrons. Now, the interesting thing is, in our case, we have SN2 plus and chloride ions. From this already, you should understand that since you're starting off with chloride ions, the chloride ions are not going to gain electrons. But according to the electrode potentials, they're supposed to be gaining electrons in this equation. But that is not happening. So you can already deduce that this reaction is not supposed to happen. But we can go further down into the reasonings and find the electrode potential to deduce. Okay, so now the question is, we know that this reaction is not going to happen. But how do we prove it using the Ecell value, or the electrode potential of the cell? So which SN equation are we going to consider? So for this you're going to take the equation where, since in this equation you are supposed to gain electrons, the other equation is supposed to be such that the reverse reaction, or the reaction, is supposed to give you electrons. It's supposed to produce electrons. So let's see for either of these equations where SN2 plus is releasing electrons. If you look at this, SN2 plus is gaining electrons. So this is not supposed to be the equation. So you can cancel out this. In this equation, SN2 plus is indeed releasing electrons in the backward reaction. Therefore, you're going to consider this value, positive 0.15. So from top to bottom, what are we doing? First of all, we check the electrode potentials, and we understood that for the electrode potential of the chloride ion, we know in that reaction electrons were supposed to be gained, but chloride ions are not gaining electrons. Therefore, we can already deduce the reaction doesn't happen. However, further off, we are going to prove it using the electrode potential values. So we know the electrode potential of chloride ions. However, we don't know the electrode potential of SN2 plus because we have two options. Therefore, to deduce which one is going to be the real electrode potential, what are we doing? We know if in one case there is gain of electrons, in the other case loss of electrons are supposed to take place. So in which case is loss of electrons taking place? For this only, because SN2 plus is gaining electrons, not releasing them. However, in this equation, SN2 plus is indeed releasing electrons. So which equation do you consider? You consider this equation and this electrode potential value. Now you can use the formula for reduction minus oxidation, E reduction, Ered minus Eox, to find out the Ecell value. So therefore, what you're going to do is, the reaction is not going to take place since the electrode potential of SN2 plus is minus 0.14 and the electrode potential for chlorine is 1.36. So the Ecell is minus 0.14 minus 1.36. So from this you get a negative Ecell value. You get a negative Ecell value. What does that mean? That basically means that the reaction is not feasible. Therefore, this reaction is not going to take place. The reaction is not supposed to take place. Okay, great. So next up, we can look into question 4. Equal volumes of 1 mole per dm cube of SN2 plus and acidified 1 mole per dm cube of VO2 plus are mixed. Write an equation for the reaction that takes place in the resulting mixture. Okay, fair enough. So for this reaction, what's happening is you're mixing SN2 plus with where did it go, VO2 plus, VO2 plus. So let's look at the electrode potential values and try to see which is going to be reduced and which is going to be oxidized. Great. So VO2 plus, where is it? Over here, and oh no, only this, right? VO2 plus, VO2 plus, and SN2 plus, SN2 plus, and SN2 plus. So how do we deduce which ones are we going to work with? Basically, we know in either of these cases, and compare these two SN2 electrode potentials, you know VO2 plus is actually going to have a greater electrode potential. So in either case, VO2 plus is going to gain electrons because it has a greater electrode potential in either of the cases. Whereas SN2 plus is supposed to lose electrons. In which case is SN2 plus losing electrons? This case. In which case is VO2 plus gaining electrons? In this case. So the equations that we choose are going to be this and this. Fair enough. So we now know the equations. Great. So how do we work with the equations? We're going to see the number of electrons. Here there is an exchange of 2 electrons. Here there is an exchange of 1 electron. So let's multiply this equation with times 2. So it's going to be 4, 2, 2, 2. So now let's add the reactants, which is in this case this, because SN2 plus is the reactant. So let's add all of these up, and let's add all of these up on the product side. So let's do it fresh. We're going to react SN2 plus with 2 VO2 plus, and we're going to have 2 V3 plus and 2 moles of H2O plus SN4 plus. So what we have done is we have added the reactants, and we have added the products. Very simple. Therefore the final equation over here is going to be 4H plus SN2 plus 2 VO2 plus is equals to 2 V3 plus 2 H2O plus SN4 plus. Great, that is your equation. Now the last question over here is they're asking you, a solution of SnCl2 tin chloride is electrolyzed for a measured time using a steady current. A mass of 2.95 grams of tin metal is produced at the cathode. Al2O3 is electrolyzed for the same time by the same current. Calculate the mass of aluminum metal produced at the cathode. Give your answer to 3 significant figures show you're working. Okay, so they're telling you that for a certain amount of charge, let's consider it X. For that amount of charge, this mass of tin is deposited. This mass of tin is produced or deposited. Therefore, we can find out the moles of tin produced. We can find out the moles of tin produced by dividing the mass produced by molar mass. So we have our moles. Good. So if you have the moles, now you know for X amount of charge, 0.025 moles of tin is produced. Great. So how do we relate this with aluminum? Now let's look at a bit of a ratio between tin and aluminum. What's happening with tin is when tin is produced from SN2 plus, and this is the chloride ions into 2. So basically you have SN2 plus as your reactants, and you know for for tin to be produced, SN2 plus needs to gain 2 electrons. Now in case of aluminum, where you have Al3 plus, and you don't need oxygen, forget about oxygen, so you need Al3 plus to convert into aluminum solid. In that case, aluminum ion is going to gain 3 electrons. Fair enough. So now you know, let's say for 1 mole of tin being produced, you need 2 electrons. However, for 1 mole of aluminum being produced, you need 3 electrons. Therefore, if you want the same mole of aluminum to be produced compared to tin, you need 3 by 2 times the charge of 3 by 2 times the charge required for tin. Why? Because for tin the charge required was x, so for each electron it's going to be x by 2, it's going to be x by 2 charge, and for 3 electrons it's going to be x by 2 times 3. This is the charge you need for an aluminum ion to convert into aluminum solid. Great. So now you know that you need 3 by 2 times x amount of charge, 3 by 2 times x amount of charge to produce the same moles as Sn. Now, do you understand the variation between the charge? Why there is a need of greater amount of charge for aluminum? Because aluminum is gaining more electrons. How many more? 1 more electron. So comparatively, how much more charge does it need? 3 by 2 into x, or the amount of charge needed for tin. So 1.5 times the charge needed for tin. But now your question is, we don't need the charge, we need the mass of aluminum produced. So how do we go there? So let's form a sort of equation using unitary method. You know, with 3 by 2 into x amount of charge, meaning 1.5 times the charge needed for tin, you can produce 0.025 moles of aluminum. You need more charge for aluminum to produce the same mole of aluminum, the same 0.025. Now what you can do is, for the same charge, how many moles will be produced? Simply take 2 to the other side, 3 to the other side, and calculate, and you're going to see the amount of moles for the same amount of charge is going to be 0.0167. 0.0167 moles of aluminum is going to be produced for the same amount of charge. Now, if the question was reversed and it asked you how much more charge do you need to produce the same mole as tin, you would answer it as 3 by 2 times the charge needed for tin. But that is not the question. So basically, what are we doing? We are forming an equation relating the amount of charge and the mole produced. We are using unitary method. Great. So now you know for x amount of charge, be it any value, for that same value of charge you're going to produce 2 by 3 times 0.025 moles of aluminum. Great. Now you multiply the moles with the mass of aluminum, and you're going to get a value of 0.448 as your mass of aluminum produced. So what did we do in summary? We used ratios and used unitary method to get to a value of moles that is produced for aluminum. Great. So that is, I guess, it for this question. Let's move on to the next question. Alright, next question is from October, November 21. So let's look at this. When dilute sulfuric acid is electrolyzed, water is split into hydrogen and oxygen. Okay, fair enough. A current of X amp is passed through the solution for 14 minutes and 462 centimeter cube of hydrogen are produced at the cathode measured under room conditions. Calculate the number of hydrogen molecules produced during the electrolysis process. Okay, great. So from this, what can you find out? You can find out the moles of hydrogen molecules produced. They've given you the amount, the volume. So what you do, divide it by the volume occupied by 1 mole of H2, which is going to be 24 dm cube or 24,000 cm cube. Great. If you know that, find out the value. This is your moles of H2 produced. Now, how do you find the number of molecules? The same Avogadro's constant. You're going to multiply the moles with the Avogadro's constant, and you're going to find the number of molecules of H2 produced. Great. Now, if the question was how many atoms are produced of hydrogen, what would you do? In that case, you multiply this with 2, because each molecule has 2 hydrogen atoms. So, I mean, they didn't ask you this, I'm just telling you this. So now you know the number of hydrogen molecules produced. How did you do that? You found out the moles of hydrogen produced, then multiply that with the Avogadro's constant to find the number of molecules of hydrogen produced. Good. Now, question B, what are they asking you? Calculate the total number of electrons transferred to produce the number of hydrogen molecules. Great. In each case, if we write down the equation, for forming one hydrogen molecule, there's an exchange of 2 electrons, meaning 2 electrons are gained. So same thing, you multiply the Avogadro's constant, not the Avogadro's constant, but the number of molecules that you found out with 2, because for each of these molecules 2 electrons were gained. Therefore 2.32 into 10 to the power of 22 electrons were used up or transferred. Great. So question C, calculate the quantity of charge in coulombs of the total number of electrons calculated in B. Very simple, you know the number of electrons, so now you multiply that with the charge of each electron, which is 1.6 into 10 to the power minus 19. You multiply, you get the answer. Great. So the answer is going to be 3.71 10 to the power 3, and that is your charge in coulombs. Great. Now the question is calculate the current X passed through this experiment. In the beginning of the question, they've given you the time. Which is 14 minutes. Good. Now they've also given you, you figured out yourself, is the charge. 3.71 into 10 to the power of 3. That is your charge. So you know the charge, you know the time, you basically find out the current. Divide the charge by time, which is 14 minutes times 60 seconds, and you have the current, which is 4.4. Good. That is your answer for question 1D, and that is the end. The other questions are for entropy, so I'm not doing it right now. Okay, good. We can move on to the next question. Alright, what is this question about? CO2 plus and CO3 plus both form complexes with EDTA4 minus, whatever that is. So use the data in the table to predict what happens, if anything, when separate aqueous solutions of CO3 plus and CO EDTA minus are left to stand in air. Great. So what they're telling you is they have separate beakers or separate solutions, separate aqueous solutions of one, let's say CO3 plus and H2O, which by the way will break down into, according to this equation, will break down into O2 plus 4H and give you 4 electrons. So that is one beaker. The other beaker is going to have whatever this is, and in a aqueous solution, EDTA. Whoa, okay. So it's going to have the same thing. Basically, the water molecule will break down into the ions, right? So you have aqueous solution. Okay. So now you have an aqueous solution in either case. So they're asking you, if each of these beakers are left to stand, is the reaction going to take place? Is water really going to break down and react with CO3 plus and give it the electrons? You don't know that. So that is what you're going to figure out using the electrode potentials. That are they really going to react? Are they really going to release their electrons and have a transfer of electrons, oxidation or reduction? Good. So the first part is, with CO3 plus, is there going to be any reaction? Let's look at the electrode potential. Which ones are we going to look at? CO3 plus is this, and the other one is this. So you have water molecules, you have CO3 plus to deal with. Nice. So if these are the two molecules that you're, these are the two reactions that you're starting off with, what are their electrode potentials? CO3 plus has a greater electrode potential, more positive. A water molecule, on the other hand, has a lower electrode potential, and we can say it is negative end. Good. Now, which one is supposed to gain electrons? Very simple. The positive end, the one with more or higher electrode potential, will gain electrons. Very good. So, is CO3 plus gaining electrons? Yes, it is. So, this part makes sense. Next part is, since this reaction has a lower electrode potential, it's supposed to release electrons. Is water molecule releasing electrons? Yes, it is. So you have a winner. Now you have two of the reactants acting according to their electrode potentials. Therefore, this reaction is indeed going to happen, where CO3 plus is reduced and water is oxidized, is going to release electrons. Great. So in this case, you can write CO3 plus is reduced, and in return oxygen is going to be produced. Yes, it's going to be produced, and this is going to happen since the E0 value of CO3 plus is greater than the E0 value of O2. Great. So you have answered the first part, which is going to hold 2 marks most likely. Now the other part of this question is aqueous solution of whatever that is it going to happen? Is the reaction going to happen? Let's figure out using the electrode potential. Okay, so what we have is, what is this? Yeah, this is the value. Let's erase the other ones. This is the value for, let's just call it Co. So for cobalt, you have 0.38 as the electrode potential. For water, you have 1.23 as the electrode potential. Great. So in this case, which is the more positive? If you have eyes, you can tell this. If you don't, sorry. So for this one, 0.38, it is going to have a lower potential, so it's going to have a negative, we can say it's a negative side of the electrochemical cell. Why? It's going to be gaining the electrons. It's going to be releasing the electrons. It's going to be releasing the electrons since it is net negative, meaning it has a lower electrode potential. It has a lower electrode potential, so it's going to have a tendency to give off electrons, whereas since it's more positive, it's going to have a tendency to gain those electrons. Great. So let's see if the reactants are according to that, is acting according to that. For the water molecules, what's happening is they are not gaining electrons. Unfortunately, they are not gaining electrons. What are they doing? They're actually releasing electrons. They are releasing electrons. If you see over here, they're releasing electrons. Whereas on the other hand, for cobalt, they're supposed to give off electrons. This is supposed to give off electrons, but unfortunately, they're gaining electrons. So this reaction is not going to happen. Great. So no reaction takes place since not feasible. O2 has higher electrode potential than cobalt, whatever that is. Okay, so that is how you can answer the questions. Good. So that is your question 1. Alright, so the last question for this video, it's rather a bit complicated and tricky, so let's look at it. This is from October-November 2017. Great. So the question is asking, an electrochemical cell consists of a half cell containing V3 plus, vanadium 3 plus and vanadium 2 plus ions, and another half cell containing VO2 plus and VO2 plus. So these ions are in one half cell and these ions are in another half cell. Great. So now they're asking you use the data from the data booklet to calculate a value for the E0 cell. Fair enough. So for one of the equations you're going to take, what are you going to take? You're going to take VO2 plus and VO2 plus. That is really hard to differentiate. Okay, so you have VO2 plus on one side and you have this on one other side. This is exactly what they wanted, most likely. Vanadium, yep, VO2 plus and VO with a charge of 2 plus. Okay, this is the one they wanted. And for this, the electrode potential is actually positive 1. The other half cell is for vanadium 3 plus and vanadium 2 plus. Which one is that? This one and this one. So that is the half cell for another, that is the equation for another half cell, which is minus 0.26. Great. So in this case, which is the more positive end? Positive one, which is with the vanadium oxide one. So in that case, what's happening is it's going to be gaining electrons. Which is going to release the electrons? This. So in this case, reverse reaction is supposed to happen. V2 plus is supposed to give off electrons, and in this case, it's supposed to gain electrons. VO2 plus is supposed to gain those electrons. Since you have only a transfer of one electron, you don't need to balance anything. You can directly add the reactants and add the products. Okay, so that is for the next equation. Sorry, next question. So for part 1, you basically find the exchange in electrode potential, which is going to be E reduction minus E oxidation. Okay, so which one is getting reduced? Which one is getting reduced? This one, which is positive 1, which one is getting oxidized? This one, since this is losing electrons, so minus 0.26, and the total value comes out to be 1.26. So for question 2, as I was saying, you add all the reactants and you add all the products. These are the reactants and these are the products. Very simple. The equations are very simple. Now they're asking you draw a fully labeled diagram of the apparatus you could use to measure the potential of this cell. Include the necessary chemicals. Okay, so they're asking you to draw the cell. A few things you need to remember. You draw two half cells. In this case, this is a metal ion half cell in either side. So what you're going to do is have platinum electrodes or platinum metals, which is going to be the surface for the electrons to travel on. Okay, great. So you're also going to have a voltmeter, you're going to have a salt bridge, and you're going to mention the ions. You're going to mention the ions, and it's preferred that you add the concentration as well, which is 1 mole per dm cube, and that's about it. So what are we doing? Voltmeter, salt bridge, the ions, and the platinum. These are the things you label and draw, and you're going to get 4 marks. Good. So next up, this one. Okay, so B, they're asking you use the data from the data booklet to predict whether a reaction might take place when the following pairs of aqueous solutions are mixed. If a reaction occurs, write an equation for it and calculate the E0 cell. Great. So V2 plus and SN4 plus. Great. Okay. So they're asking you if the equation is supposed to take place. So let's see the chart, and we're going to figure out the electrode potentials. We're going to compare and see if the reaction is really going to take place. So SN4 plus and V2 plus. Where do we have SN4 plus? Here we have SN4 plus. Do we have SN4 plus anywhere else? No, we don't. And the other one is V2 plus. V2 plus is available over here and over here. Interesting. So we have two values for V2 plus, these two, and Sn4 plus is only available in this electrode potential. Now very easily you can say, since tin has a more positive electrode potential compared to either of these equations, you know Sn for this electrode potential, electrons are supposed to be gained. Electrons are supposed to be gained. Is Sn4 plus gaining electrons? Yes, it is. So this part of the equation, electrode potential reaction is correct, is accurate. Good. So this is confirmed, and let's move on to the next two parts. How do you decide between either of these electrode potentials? Very simple. You know, here there is a gain of electron, and in the other one, gain of electron, and in the other two, you're going to have a loss of electron from vanadium 2 plus. Where is vanadium 2 plus losing electrons? Over here it's gaining electrons, so cut this off. Which one is gaining? This one is which one is losing? This one is losing. Vanadium 2 plus is losing electrons in this equation, so you take which value? This value and this value. Now what did they ask? Yeah, so it's going to happen. Why? Because this does indeed match. Here it's a forward reaction, here it's a backward reaction. So this reaction is going to take place. Great. So you write yes for the equation. What do you do? Over here there is a transfer of 2 electrons. Over here there is a transfer of 1 electron. Very easy. Multiply with 2. Multiply with 2. And then what do you do? Add the reactants, which is these and these. Okay. So you're adding these and these. Great. So add those up and form an equation, which is this. Great. That is your equation, ionic equation. Very good. Now how do you find the Ecell? E reduction minus E oxidation. Good. What do you do now? Take the value of reduction, which is getting reduced, 0.15, which is getting oxidized, minus 0.26, and you're going to get a total value of 0.41. Great. That is your answer. Now you have vanadium, whatever that is, VO2 plus and Fe3 plus. Now what's going to happen over here is you have a lot of equations relating to that. So let's look at equations relating to VO2 plus and Fe3 plus. VO2 plus, where are you? Charge of 2 plus, charge of 2 plus, charge of 2 plus, charge of 2 plus. For iron, what do we have? Fe3 plus, we have Fe3 plus, Fe3 plus, and what else? Most likely that's it. Yep. So these are the 5 electrode reactions we have. Great. So how do we decide for which of the reactions we are going to calculate and figure out if the reaction is feasible or not? We are basically going to deduce. Try and see which one makes sense. So let's start off randomly. Both of these are relatively small, and one is negative and one is positive. Fair enough. If we look at over here, both of these, very interesting, have the same electrode potential. Fair enough. So let's compare it. Positive 1 for either of these, positive 1 electrode potential, 1 volt, and for these it is either minus 0.04 or 0.77. Are these lower than this electrode potential? Yes, it is. So if it is indeed lower than that electrode potential, we can see that in either of these cases, Fe3 plus is supposed to lose electron. Fe3 plus is supposed to lose electron. Does Fe3 plus lose electron in either of this case? No, it does not. It is rather gaining electrons. So this does not make sense. Again, for these cases, since it has a more positive electrode potential, these are supposed to gain electrons. Are they gaining electrons though? No, they are not. They are rather releasing electrons in the reverse reaction. They are releasing electrons in the reverse reaction. Great. So let's compare these iron with this value of VO2 plus, this one. In this case, what's happening is VO2 plus is gaining electrons. Let's see the electrode potential. The electrode potential compared to, let's say, one of these iron is actually greater. So this is supposed to gain electrons. Is this gaining electron? Yes, it is. But since iron has a more negative electrode potential, it was supposed to lose electron. Fe3 plus was supposed to lose electron, but it is gaining electron. So no, this is not going to happen. If we take another example, this, and compare it with this, VO2 plus will have a lower electrode potential and Fe3 plus has a greater electrode potential. So VO2 plus in this case should lose electron and this should gain electron. Is VO2 plus losing electron? No, it's not. And is Fe3 plus gaining electron? Yes, it is, but only this part is correct. This part is not correct. So the moral of the story is, in this case, no matter what combination you take and try to make them react, it's not going to take place. At least one part of the half cell equation is not going to be taking place. Therefore, this reaction is not feasible. This reaction is not feasible. So what do you write? No. And keep this as not applicable or just blank, because the reaction does not happen. Great. So only this part was a bit complicated. You have to look at all the equation. I don't know if there's a shortcut, but yeah, that's how I did it. So yeah, that's it for this video. Hope it helped you. See you in the next video.